Hello, everyone. Welcome to the Mindscape podcast. I'm your host, Sean Carroll. So, physics, it's in a crisis. Have you heard that? Have you heard that physics is in crisis? We're in trouble because we haven't found new particles. Supersymmetry and string theory and dark matter have been proposed as these wonderful theories, but no experimental evidence has yet been brought forward that these might be on the right track. We are lost in our own thoughts, sitting in our armchairs rather than confronting the reality of the world in a direct way. Or so we are told. I don't think it's quite that simple. I don't think that physics is in a crisis, but there is something really, really interesting from the kind of history of science point of view about the present moment in fundamental physics, in particle physics and cosmology, namely that we are really, really good at explaining the data. You know, we have theories, the standard model of particle physics, the core theory, general relativity, the standard model of cosmology. We're almost too good. We have these theories that fit all the data we have. But also, we think we have really good reason to believe that these theories are not the final answers. It's easy to come up with questions we can ask. These theories don't provide sensible answers to. So that puts us in a bit of a pickle in terms of how to make progress, right? I mean, we would like to build bigger and more powerful instruments to probe the natural world, whether they be particle accelerators or observatories, dark matter detectors, etc. But we don't know exactly what we're looking for. So where are we? Why aren't we somewhere else? Are we driven to questions like the multiverse and the anthropic principle? Is it okay to be driven there, or is it somehow embarrassing to be driven there? That's what's on the table today. We have as our guest Michael Dine, an extremely distinguished particle theorist. Michael is maybe the leading person over the last few decades at taking ideas from big picture questions about string theory, supersymmetry, etc., and connecting them to experiments, things that we can try to observe in accelerators or elsewhere. As he will very, very quickly admit, we don't have the data that we would like to have had, so he hasn't, made a prediction that has come gloriously true, but he's a very, very reasonable guy. Michael is very optimistic about particle physics in general, but he's also absolutely willing to admit that there are challenges ahead of us, to admit that string theory, for example, or supersymmetry, as successful as they are intellectually, haven't lived up to the promise of their early years, and maybe that's a reason to rethink a little bit. But of course, as he would say, give me your better idea, and then I will start rethinking. So we have a long conversation that goes into a lot of what is the big landscape of issues confronting particle theory and fundamental physics more generally in the modern era, where we are, where we hope to be, how we might move forward, covering a lot of different possible ideas. It's a very good overview that should give everyone a balanced picture of what is in the mind of most working quantum field theorists, particle physicists, fundamental physicists. And I say that very carefully because, of course, the public view isn't always the insider view. You're getting the insider view today. Not everyone agrees because this is, still academia, still science. We disagree with each other, but you're getting what basically is the closest to a consensus view of what state particle theory and fundamental physics is right now. Feel free to disagree, of course. Michael is very clear when he doesn't even know what the answer is himself, but we'll learn about what that state is, maybe give us some clues for going forward. If you want more depth and details, he has a new book just out, This Way to the Universe, a theoretical physicist's journey to the edge of reality. So let's go. Michael Dine, welcome to the Mindscape podcast.
Very good to see you, Sean.
I thought we would start simple, down to earth. Tell me, what is the state of elementary particle physics today? How would you summarize it in a few words?
Well, of course, that's I wrote a whole book about this, but what I would say is that it's in one sense in a remarkably good state. We know an awful lot, a lot of things that seemed well beyond us 20, 30 years ago. We have also many questions. Some of them are things that we are likely to know answers to in the foreseeable future. Some maybe longer, and some possibly never. and it's that, and there's some tension. There are in that kind of division. There's a tension, and what will we really know? What are the questions we should be asking? What are the questions we'd like to ask? That's, I think, kind of what I see as the status now.
Well, it's a remarkable success story, right? I mean, the whole framework of quantum field theory, which we now take for granted as the right way to describe elementary particle physics, there was a time in the 60s, maybe even the early 70s, when people were doubtful about that, but then it eventually triumphed.
Oh, absolutely. One of the things I talk about a little bit.
I'm sorry. I'm still hearing your alerts.
Yeah,
and they're quite loud.
Let me repeat that, I'm sorry, I have not been able to suppress this properly. One of the things I talk about in the book a bit is that when I started out as a graduate student, quantum field theory was still just a little bit on the edge. There were other ideas around. String theory in its first incarnation proposed a whole different way of looking at elementary particles than quantum field theory. And there was still a lot of interest in the subject. So it was just at that point that the standard model with its various features was taking off.
Mm-hmm.
And it wasn't totally established then. So that's certainly something that's changed. And all of, we've gone from very tentative understanding to precision understanding of the strong interactions, the weak interactions, the electromagnetic interactions. And that's certainly not something that we envisioned in, say, the mid-1970s when I was kind of starting out.
Well, we don't have to go into, I think, like listing all the particles and forces, but it's important to get on the table, I guess, that there is a set of particles and forces that we think is more or less internally complete, right? I mean, maybe there's more particles and forces that we haven't found, but there's none out there that we say, oh, we need this one ingredient to make things make sense.
That's right. So in some sense, so I should back up and say that as an example, first I should say that there are sort of three forces that we deal with commonly in experiments: the strong, the weak, and the electromagnetic force. Okay. And those forces, we've come from this very tentative understanding 40 years ago, say, to a very precise understanding now. And that's in some sense a good and a bad thing. It's a great thing in the sense we have this understanding. For working scientists, it's a puzzle. Everything works almost too well. We have questions, and it's not clear we have good clues to the answers. So I think that's again a sort of tension that I think I tried to deal with in this book. That what is it we understand, what is it we don't understand, and what are the clues we have to answering the questions we don't understand. We certainly don't know everything, but we know an awful lot.
Yeah, I mean, sometimes the way I put it is we have a theory that fits all the data, and we know the theory is not right. And that's a very frustrating position to be in as working scientists.
I think that's a very good way to put it, yes. I might borrow that slogan from you from time to time.
Please do. And I mean, maybe, again, for the people who are not experts in this, let's try to make sense of the discovery of the Higgs boson, because that was a big, in 2012, on the one hand, a tremendous amount of anticipation. It all worked. The Large Hadron Collider did a great job. On the other hand, there was a sense in which we expected it and would have been much more surprised not to have found it. So, I mean, how do you think about that achievement 10 years ago?
Well, in a sense, for me, there are two aspects of this. One is that basically in the mid-1960s, Steven Weinberg and Abdus Salam wrote down a theory of the weak interactions with a particular structure for the Higgs particle. Okay, there was they did the simplest thing one could hope to do. There was no particular good reason that should work.
Yeah,
and there's been a lot of angst in the subsequent years about whether that would be right, whether it should be that simple, whether really you might expect some more complicated sort of story. And so in a sense, it's remarkable that simple story which has various peculiarities. It raises some of the questions which you and I sort of alluded to now. That simple story works. So from my perspective, that's what's really striking. So I have colleagues, for example, who work on the question of both experimentalists and theorists who work on the question of additional Higgs particles. Could there be more? What is true about that is if that were to be the case, that's really weird. That in terms of the kind of puzzles that we have about the Standard Model, it's weird enough that there's this one simple Higgs. Okay, and if there were more, that would be really striking. So I tend not to be an enthusiast for these possibilities, but I do sort of view them as, well, if there were a discovery, it would turn my world around.
Maybe one thing that would be worth remarking on, or I would love to get your insight into, is when we talk about the Standard Model of particle physics, we're excluding gravity from that. Sometimes, following Frank Wilczek, I lump in gravity and call it the core theory because we understand quantum gravity in the weak field regime pretty well. But of the three forces that we know, the electromagnetic, the weak, and the strong, they're all in different phases, as quantum field theorists call them, right? The Coulomb phase, the Higgs phase, the confinement phase. Talk about, I'm assuming that the people in the audience don't know what those words mean necessarily, but talk about what those words mean, and is it interesting or provocative to you that the different forces are manifesting themselves to us in different phases?
Well, I should say, for me personally, this is very interesting. And I'm going to say a few words. I'll say a few words about this. So for me personally, what I was keeping me awake nights these days is exactly question of this phase structure, and in particular the phase structure for the strong interactions. So again, this sort of takes us back again to my graduate student days and all the things that have happened subsequently. So in my graduate student days, people understood or felt they understood the electromagnetic force, which, as you say, is something in Coulomb phase. It's the phase which means basically that we have charged particles. They repel each other if they have the same charge. They attract if they have the opposite charge. All those features are sort of familiar, and we understand this in very detailed ways, and with quantum mechanics and quantum field theory.
Right.
So that story we understood. In the late '60s, we have this development of this story of the Higgs phase, which is the phase of the weak interactions, and we understand that the gauge fields, the particles that mediate the force, are heavy. And that's in contrast to the Coulomb phase of QED, of quantum electrodynamics, where the photon is massless. And the photon we know is massless to an extraordinary extent. And it's at some point, people believe that was forced on you by questions of principle. And the Higgs particle, so the Higgs really was discovered by a gang of 6.
Yeah.
Higgs' name got attached to it for historical reasons. But what they discovered is a mechanism by which these force carriers can be heavy. The strong interaction in those days in the 70s was even a bigger puzzle, because so people predicted the existence of quarks, and that quarks had forces mediated by these particles called gluons, okay, which should be massless.
Mm-hmm.
And then the question is, why didn't you see the quarks, these fractionally charged particles, and why didn't you see the gluons? And so in those days, people started talking about something called confinement, that somehow the quarks weren't visible. And this sounded preposterous, a sort of excuse for something. And I think even those who said these words were very uncomfortable with the situation. That's changed a lot. We've understood that this sort of confined phase of a quantum field theory is a real phase of the theory. And we have various tests. We have theoretical tests on paper with paper and pencil, but we also have numerical simulations, very elaborate numerical simulations, so-called lattice gauge theory computations, which verify this feature, this confining feature. And there are interesting relations between the confined phase and the Higgs phase in particular, because in both cases you don't have a massless force carrier that you can see. So sometimes these phases are really kind of opposite sides of the same thing.
Hmm.
So this is, again, something where there's been enormous progress. And again, something which keeps me awake nights is trying to understand and absorb some of the results of the numerical studies, of the computer simulations of the strong interactions, which at this point, which again in the 70s were in a very primitive stage, both because computers were primitive compared to what we have now, and also because the algorithms and the theoretical understanding was much poorer. And the level of sophistication now is quite extraordinary. I mean, the lattice people not only verify things we sort of think should be true, but they predict new things and new phenomena.
It's a good point because it's something that's hard to appreciate maybe from the outside, because in the early 70s, people, like you say, would say things like, oh, there are these new particles called quarks, and they're held together by particles called gluons, but you'll never see them. They're hidden inside other particles. And
Right.
other people, like you say, they're rolling their eyes. But now, yes, we've more or less established that's what happens. Not to the level of a rigorous mathematical proof, but our level of understanding has increased enormously, even though what we're saying is, yes, those guesses back in the 70s were correct.
Right. I mean, what I do tell my students is that still really proving it at the level of a sort of paper and pencil mathematical proof is a subject of one of the so-called Clay prizes. You can collect, I believe it's $1 million. Maybe the amount has changed over time. I'm not sure. You can collect $1 million if you show up with a proof. That's been out there for about, I guess, 20 years or so, and it hasn't happened yet. So we're still very reliant on very elaborate numerical studies, computer studies, for which, it's sort of like, someone tells you this, they did this big computation, and this was the answer. And you don't have a lot, physicists would like, I mean, all of us would like to have some simple conceptual understanding of what's going on.
Right.
And when I say simple, I don't, I should be careful a little bit. I mean, I sort of try to explain both. There's a notion of simple, which is which sometimes we think about simple as quickly I can give you an answer. There's a notion of simple in the sense that I could give this as a problem to a very good graduate student, and they could take them 3 weeks and they would come back with an answer. That's something I would call simple,
Right?
Okay, as opposed to something which you have to spend a lot of years of your life and millions of dollars of computer time and equipment and so on to solve. So there's a notion of complex or difficult, which is sort of technical, which is saying it's not just being smart or being clever, it's being needing some serious resources to solve it.
Well, I'd like to give the podcast episode audience some homework. So if any of them want to prove analytically that quarks are confined in the strong interactions, they would win $1 million, and maybe they could donate some of that to the podcast. So now they've been informed of that. But I guess what I'm wondering is, since we're here to sort of think about how to move forward in particle physics, we have these three phases. The strong, the weak, and the electromagnetic interactions all look different to us. It took us a while to figure them out. So number one, are there other possible phases that quantum field theories could be in that we just didn't get lucky enough to see in the real world? And number two, should we be surprised in any way that the three forces that we have in the standard model are all very different?
Both are good questions, and I'm not sure I have a good answer. I would be hesitant to say that there can't be other phases. I mean, there are things that we've learned about quantum field theories that are surprising, and there's surely more to learn. I mean, looking, my colleagues who in condensed matter physics and those who follow condensed matter physics, certainly there are phenomena there that I won't claim I have much understanding of or knowledge of. Which are different,
Yeah,
and whether some of these could have realizations in the kind of quantum field theories that obey the principles of Einstein and so on. I'm not sure I'm competent to say.
Okay.
the I don't think, if I look at the kind of range of ideas that are out there for new physics beyond the standard model, I don't know that there's, well, I should be a little careful there. I mean, I think there are probably people who talk about other sorts of phases. They might be variant of things we know. So I should probably be a little careful there. But most of those ideas sort of fall within the realm of these phases we know. Now, whether the question you ask about whether it's surprising that the laws of nature that we know encompass these three possibilities, it probably gets back to the first part of the question, because it could be that, yes, isn't that amazing? There are three possibilities, and they're all exploited by the laws of nature. And it could be, well, there are three possibilities we know because there are three possibilities that are realized in nature and in the experiments we understand.
Well, that it leaves us with a good open question then, I guess. Speaking of which, back to 2012 when we found the Higgs boson at the LHC, I know that a lot of people, certainly me, probably you, were anticipating finding a lot more things at the LHC. Were you surprised that we haven't yet already? How much of a realistic expectation was it that we would find not only the Higgs boson, but other particles as well?
Well, this gets to, I should say, in my own career, I went through phases on this question. So if you'd asked me this question 20 years ago, I would say, oh, almost for sure we're going to find something new. And I had a list of possibilities, supersymmetry, something called technicolor. And the reason was connected with this thing called the hierarchy problem, which I don't know if we'll talk about a little bit. So we had a particular reason. And it's related again to the fact that the simple Higgs model was just in some ways too simple. It's very hard to understand why, if there's just the Higgs particle, the standard model, it's as light as it is. Now that's a little weird because of course it's very heavy and took several $1 billion worth of equipment to find it. But really, it's hard to understand why it isn't orders of magnitude harder to find. And what we were aware of, what we became aware of in the early 2000s, is that there's another puzzle of this nature. And this is the thing that gave me pause about the hierarchy problem. And this takes us to gravity, as you alluded, this other force which plays obviously such a big role in our very existence. So in gravity, in Einstein's theory, so I'm thinking of gravity as described in your wonderful textbook. In Einstein's gravity, there is a possibility of something called a cosmological constant. This is something Einstein contemplated early on when he first started to think a little bit about the universe as a whole, and thought about including it. Then with Hubble's measurements of the expansion of the universe, discarded it, called it the greatest mistake of his life, something like that. But in fact, we know it's there. And we know it's there in a large amount in the scale of our universe today. It's 70% or so of the energy of the universe, but a very tiny amount compared to what you might guess it would be a priori. And the truth of the matter is we don't have any great ideas for an explanation for this fact. Okay, it's certainly one of the things that I view as, and most of us view, as one of the great puzzles in physics. It's something which by the early part of the millennium we had measured. I mean, of course, the humanity collectively.
Right, not you and I know.
Yeah. And it's very puzzling. And this fact that there's this other puzzle, which in many ways it has some of the same characteristics of the puzzles of the Higgs, certainly gave me pause. And gave me pause that any of the sort of rational explanations which people were thinking about for one problem could be what we're looking for. In other words, we didn't have a good explanation for one. Why should we think we'd come up with a good explanation for the other? And in fact, this probably gets to your earlier question. I think this is the thought I lost here, that one of the explanations that people offer for this is this so-called anthropic explanation. So for the cosmological constant I'm speaking of, which is that basically somehow the universe selects from possible laws of nature those laws which permit the existence of intelligent being. Okay? This is a very I'm not going to advocate for this here, but just it's very disturbing. The problem is that for the cosmological constant, it's about the only game in town. It's about the only explanation we have. Okay? So you could ask, well, so I certainly was worried before the LHC turned on about whether there was something like that going on for the Higgs phenomena, for this question of the hierarchy problem. Getting back to your earlier question, in fact, about why are there these three realizations of the gauge principle, of the gauge symmetries in the strong, the weak, and the electromagnetic force, that might also have something, in common with this. It may be that, in order that we have a sensible universe in which we can form complicated nuclei, as iron, carbon, and so on, we need the strong force to have some of the features that it has. And in order that stars evolve sensibly, the weak force has to have some of the features that it has, and so on. It's a very disturbing form of explanation, but it does but it's precisely because it's disturbing, it raises worries about what it is we do and don't understand, and what it is we can hope to understand.
Let's take this seriously, because you put some big ideas on the table here. Let me try to summarize and see if I got it. We have this puzzle. Why is the Higgs boson so liked? Or why is the hierarchy problem? Why is there a difference in energy scale between whatever the Higgs boson is doing, what we call the electroweak theory, and higher energies of unification or gravity? And most explanations we had on the table would have predicted new particles you could see at the LHC, and so we were optimistic. But then we realized there was this other puzzle that was similar in spirit to the hierarchy problem, namely the cosmological constant problem. Why is the energy of empty space so small? And there, you didn't quite say this, but correct me if I'm wrong, we don't have on hand a bunch of plausible explanations that would have predicted other particles or anything. The best explanation we had was this anthropic idea, and that raises the specter that the anthropic idea is also responsible for the Higgs and wouldn't predict any new particles.
Right. Absolutely. I should say, a lot of people, there's a lot of hostility to this anthropic idea, and for good reason. I'm sympathetic to it, but it often starts out by saying this is unscientific. But what is remarkable is that, in fact, at the time that Steven Weinberg, who really was the person who sharply formulated this question for the cosmological constant, or the dark energy, put this forward, there was no evidence, no sharp evidence, certainly, for a cosmological constant. And he said, well, since it's so hard to explain why it should be small, what it should be is the largest value consistent with the existence of intelligent observers. And he didn't do it in terms of people, he did it in terms of formation of structure of stars and galaxies and so on. So he actually made a prediction, and the prediction wasn't perfect numerically, but it wasn't too far off.
Yeah.
In a sense, again, I try and sort of describe this in the book in a sense which is actually remarkably good. So he made a prediction, and the prediction was verified. And so it sure looks scientific to me. It may be wrong.
Mm-hmm.
It may make us ill, but it's really there. I mean, I should say, in terms of my expectations, I think one of the things I talk about a little bit in the book is when I first confronted this question of the cosmological constant. So this was thanks to Leonard Susskind at Stanford, and
former Mindscape
it was a time
guest.
when we were working. Yeah, and it was a time we were working on. I was working with a colleague, Willy Fischler, on supersymmetric models to explain the hierarchy problem. And we had succeeded in various ways, which were new, in making models of this type. So we were very excited. We thought we'd solved the problem. And Lenny came up to us and basically said, well, what about this cosmological constant issue? And I had never thought about it before. And I should say, by the way, it was Lenny who introduced me, as I also explain in the book, to the hierarchy problem. So it's like, so again, I was sort of shaken, and so Willie and I said, well, we better solve the cosmological constant problem. So we banged our head for a few weeks as if that was enough.
Yeah,
and
it's harder to do.
Too successful, but certainly this as an issue. So it's obvious. First of all, the issue is not original with me, certainly, and as a lingering issue has been around for again the better part of 40 years. And
I mean, maybe let's get on the table what you need to make the sort of anthropic solutions work, right? I mean, you're asking a lot, and this is part of. I'm willing to consider anthropic solutions myself, although I share your maybe not even disdain, but sort of disappointment that we can't get a unique solution to these things.
Right.
But you need kind of a multiverse, a lot of different possibilities out there, and then you look for the little subset where people can live.
Right. So in a sense, this is the way that, you could start with the principle and say, you can imagine there's an omnipotent being that, wants to create people, and so adjust the laws of nature with some dials and so on until people pop out. But that's certainly not a very satisfying form of explanation for most of us. I think even for people who are religious and so on, it's too much. What Weinberg had in mind was something like the possibility that there is this multiverse, that there are many possible universes. What exactly that means is a question that you probably understand better than I, and probably don't understand that well either.
Right.
But in some sense, there's some multiplicity of universes, and that somehow we can sample them. Okay, and that in most of those, there won't be, as Weinberg says, in most of those, there won't be stars or galaxies, much less people. Okay, in some very small subset, he said, you will grow structure, you will develop galaxies, stars, planets, and so on. Once you open this Pandora's box, you start worrying about other things. When do you have carbon-based life? It gets kind of scary, and it does in some sense run the risk of becoming unscientific in the sense of how do you decide what does the sample look like?
Right.
So Weinberg did something very crude and simple, and in its way rather compelling. If you open up when you open up this box, it gets a little scary. I mean, how you actually and I have to confess, I'm guilty of trying to figure out what it might look like, and it's a tough problem.
Yeah, and so is it plausible? So it's very I shouldn't say very clear, but it's relatively transparent to me how if the energy of empty space were radically different, it would be hard for us to live, hard to get stars and galaxies. But what about the Higgs boson? That's the other problem. Is there any sense in which if the Higgs boson were as heavy as we think it should be, life couldn't exist? Or is that a more subtle kind of argument that presumably depends on what you mean by life and complexity and atoms and so forth?
Well, it's possible that already processes in stars are sensitive to features of the weak interactions, for which the Higgs particle and the Higgs phenomenon are the controlling feature.
Mm-hmm.
So if the Higgs particle were extremely heavy in the way we think it by rights should be, then arguably the particles which mediate the weak force would be massless, like the photon, mm-hmm. and they would not mediate the sort of interactions we see in the weak interactions. So they would not involve processes that change protons into neutrons and neutrinos and electrons, for example. The things that the weak interactions do, which are very critical to the way stars burn and evolve. So there are people who've thought more seriously about this than I have, but I think you start with processes in stars, and even before you get to people, just the burning in stars and so on would be quite different. Whether you could sustain stars or not, under what circumstances, you need somebody with a better astrophysicist than me, probably you,
Better than
but
me.
to sort of enumerate the possibilities. But a lot of them don't come close to anything like the universe we see around us.
So I guess this was probably oversimplifying because I had not thought about this deeply myself. I'm a little skeptical when people try to pretend they know a little bit more than they do about what counts as life and complexity and intelligence
Right.
and so forth. But
Right.
but I guess if there were this kind of mechanism, it would be, we need some amount of complexity in the fundamental interactions of particle physics
Right.
to give rise to complexity of big macroscopic systems.
Right.
And we have that in the standard model, in part because we have three different forces that behave in three different
Right.
ways.
No, I think you put that very well.
And maybe that's like the minimum you need. And maybe that's therefore not surprising that this is what we see
That's
in
right.
nature.
Yeah, no, I think you put that very well, better than I put it before. I think about there was, this notion of carbon-based life, for example, I remember was a sort of half joke years and years ago of Carl Sagan's about maybe we'd land on Mars and we would see silicon giraffes. I think it would roughly went like that. So, so certainly so that's just within kind of thinking about the complexity you might develop within chemistry as we know it.
Mm-hmm.
And who knows about chemistry as we don't know it.
Yeah, sure.
But I think you put it well that the three forces we have do provide somehow a framework which allows for very complex structures, the sorts of things that might be necessary for life. When you get into this anthropic kind of story, I should say, by the way, in some sense, people make fun of it and so on. There's a certain level in which it's really a lot of fun. And
let's let ourselves have
kind
fun.
Of intriguing. What are the alternatives
Yeah.
you might imagine? What are you willing to contemplate? I mean, so on the one hand, it does quickly take you out of the realm of something you can sensibly ask scientific questions about, in the sense of go out and do an experiment. Let's check this. But it is interesting. I do think of it as kind of like a resource for homework problems for students or something.
With that in mind, and I think actually, we sketched out a plausible story. It's not that crazy, but maybe it's not right either. So obviously, as good scientists, we want to think about the alternatives. So let me get your ideas about what might be going on just beyond the standard model that might be experimentally accessible in some ways. And I'll let you say what you actually think, but first let me ask some sort of obvious questions. We have families of particles. We have the electron and its neutrino. We have the muon as neutrino, the tau and its neutrino. Likewise for the quarks. Could there be families beyond what we see? We have three generations. Could there be a fourth generation of particles?
Well, we have some constraints on that. So the answer is yes, with some buts or asterisks. So it's probably not, if there's a fourth generation, it's probably not exactly like the other three. So we have some constraints on the number of neutrinos, for example. So probably any neutrinos in a fourth generation would have to be heavy. I should say, by the way, maybe back up and say in a generation, as Sean said, there are two types of quarks. There is a charged lepton, like the electron, and a neutrino, and that structure repeats. So we have the up and down, the electron and its neutrino. We have the charm quark and the strange quark, and the muon and its neutrino, and we have the bottom and top quarks, the tau lepton and its neutrino. So those are the three generations we have. We probably can't repeat exactly that, but could there be others? Absolutely. And so, for example, in string theory, the kinds of things people do, they're sort of games that people play. They're not really predictive in a reliable sense. But often there are more. Okay, but some of these things really have to be well hidden, or they disrupt the phenomena we know in astrophysics and cosmology, for example. So there are things we know. There are also things about particles we know. The properties of the Z boson, one of the weak interacting gauge bosons, would be disruptive if there are more neutrinos. But but one of the things one of the places in the book where I sort of dare to make some statements is one of the extensions of the Standard Model that people have talked a lot about is supersymmetry.
Mm-hmm.
And one of the disappointments, and certainly I checked it at some point or other, I may have even given the number in the book. There are thousands of papers with supersymmetry in the title. It's been a big industry. And I was certainly a participant in much of that, and I will defend what I did there. But one of the disappointments for those who advocated supersymmetry was something which, among other things, did several things. It provided a possible solution to the hierarchy problem. It offered an explanation of the dark matter, and it offered some possible explanation of the strength of the forces. So it was quite remarkable.
You should tell us what supersymmetry is.
Okay, good. I should back up. So this is related to the story I told about Lenny Susskind and the hierarchy problem and the cosmological constant problem. One of the question is really sort of why is that single Higgs boson there just sort of hanging out by itself? It really has almost no right to be around and to be as light as it is. And so one of the explanations was maybe there's a symmetry principle, maybe there's a ground principle that says the Higgs boson can't be too heavy. And supersymmetry was the candidate for that principle. So first of all, what does it mean to be a boson? Okay, a boson is a particle with integer spin, either zero spin or spin one, like the photon, for example. The graviton in Einstein's theory would have spin 2. Okay, so particle with integer spin. A fermion are particles like the electron, the neutron, the proton, particles of half-integer spin, and which are distinguished by the fact that they obey the Pauli exclusion principle. Okay, bosons obey a different set of rules, okay, developed by Bose and Einstein, and these bosons are puzzling. The gauge bosons not so much so, but the Higgs boson, yes. The particles of spin 0, yes. Now it turns out that particles with half-integer spin don't create this puzzle. That they can be light with no problem. So this is a feature of quantum field theory, something that's well understood. People thought about this issue already in the 30s. So that part's well understood. So what supersymmetry was a symmetry between the particles with half-integer spin and the particles of integer spin. Okay, and the fact that the half-integer spin particles could be light meant also that the particles with integer spin could be light, and in particular the Higgs boson. Okay, how light? Well, it turns out about as light as the gauge bosons of the weak interactions, the W and Z. Okay, maybe a bit heavier. Okay, and so that was the reason. That was sort of why a lot of us thought you should see the Higgs boson before we built the LHC.
Mm.
Okay, got a little worried that it hadn't been found, but said, okay, maybe it'll be found there, and it was found there. Okay, but the supersymmetry, the stuff that comes with it, was not found. Okay, and that's really was really troubling. Okay, and basically what we would say is that in order to understand if the particles associated with supersymmetry, the partners of, for example, the W and Z bosons, which would be some heavy fermions, if they are as heavy as they have to be now, as we know from looking for them from the LHC at the LHC, if they're that heavy, that means that there's something peculiar about the theory, that numbers in the theory, the constants, the constants of nature that control that theory, have to be adjusted in just the right way to make this work. So if you're as old as me and you can remember radios with dials which you adjusted, you have to adjust them to extreme precision,
right,
to get things to come out. So that's the problem. So one thing that I think is maybe true is maybe that's okay. Maybe the particles are there and they're just a little heavier. And one of the reasons I give for this has to do, actually is related to this multiverse picture. Okay, So in the multiverse, one of the things that's interesting about a multiverse, again, is a very troubling idea, but it's also really interesting. And one of the things that's interesting is that you have universes with very different energies. And higher energy states, higher energies now, this is energy per unit of volume. Higher energy states can decay just like particles can, and just like atoms can, to lower energy states. And so now you have a question. You have all these states. Why are they stable? Why do they live a long time? They have to live a very long time. The age of our universe is enormous compared to the time it takes light to cross an atomic nucleus, for example, which is a kind of characteristic time we might think about. And so why would that be? And it actually is very hard to come up with a robust explanation that sort of explains why, among these many things that, for example, our universe could decay to many, many different lower energy universes, why can't we decay to any of them? Or why does it take so very, very long time to decay? And about the only explanation that really works well and is really kind of robust is supersymmetry. So supersymmetry, it turns out, this may be something in your textbook somewhere, is something that protects these states. Now, supersymmetry would not be exact because the partner of the electron, for example, is at least too heavy to see at the LHC. Okay, so supersymmetry is a broken symmetry, but it turns out that's good enough that the universe could live for a very, very long time if that were the case. And I have sort of speculated that maybe we're just been a little unlucky. Supersymmetry is sort of around the corner, a bit higher than where we thought it would be. And I think that, well, this certainly sounds like making excuses, and it is. I think this is one possibility. And what's interesting is to ask, there is one handle, I should say, on this number, which is the mass of the Higgs particle itself. So if nature is supersymmetric, given the mass of the Higgs particle, we sort of know where supersymmetry should be, roughly. And it's possibly within reach, just barely, of the highest energy accelerators that people talk about for the future.
So in other words, not to be too unfair about it, but to simplify, many people who liked supersymmetry, especially as an explanation for the hierarchy problem, did expect to have discovered supersymmetry by now at the LHC. But that hasn't happened. It could have happened already. And what you're saying is there's still sensible reasons to think that if we keep looking, we might find it.
I think that's right. Now, this is a lot to ask of people,
funding
both the
agencies.
general public to fund some international scale, $10 billion plus scale project to do this, and for scientists to devote years and years of their lives to a search with no guaranteed outcome. So I don't want to overstate this case. I don't want my friends to go out or come back to, by the time they come back to me, I won't be here anymore. But I don't want my friends to go out and work so hard for in a pursuit which is not by no means guaranteed or probably doesn't even have high probability of success. But I do think this is a possibility. Maybe I'll just leave it at that.
Okay.
It's
Well, I know that supersymmetry is the most popular probably theory or framework for going beyond the standard model. But let's just check off some of the others so that people out there know how they stand. And we talked about it's difficult to add new generations of particles. What about new layers, right? We discovered that protons and neutrons are made of quarks. Is it possible that quarks and leptons are made of even tinier particles?
Certainly possible. It's challenging to build theories of that kind. And I think I've developed a sort of prejudice about that class of ideas, largely from thinking about string theory. so one of the so string theory uh, is really probably in some sense a class of theories of elementary particles of strong, weak electromagnetic and gravitational forces. Uh, and we can ask sort of but it is remarkable. It hangs together really well, at least in certain ways. And a lot of the problems that we see when we try and combine general relativity and the standard model are resolved. There are lots of questions that are not well answered, and again, I'll advertise my book for that in terms of, I think, talking honestly about what some of the issues are. But at the same time, it is kind of a template for what an ultimate theory might look like, and it really does have things like quarks and leptons and gauge bosons, the things we see. It often has other stuff. That's probably good, but because we need other stuff to resolve other questions. But it doesn't, in any obvious sense, point to something like further substructure.
Yeah. Okay.
Now, that doesn't, and that plus the fact that it's hard to build theories with further substructure, sort of prejudices me, I guess, a little bit against that. Could it be? Absolutely.
But okay, I mean, let's stress that you're giving two very different sets of reasons for why you're not enthralled by these theories. One is that you have a belief that we should give a lot of credence to the possibility that something like string theory is behind the whole story, and string theory does not lend itself. But the other one is a purely empirical thing that, given what we know about the data in particle physics, it's just hard to build models with this kind of substructure.
Yeah, yes. So this is a point. The second point, which is different, was a point that was originally sort of formulated clearly by Gerard de 't Hooft, who, again, a long time ago, in the late 70s, when people were speculating that, well, there are quarks and there are leptons, why shouldn't the quarks be built of other things? Preons, they were called, other kinds of names. And de 't Hooft put forth a set of guiding principles for such a program. So basically, he said the puzzle is when you put things together, why do you get things that are light or without mass altogether? So light things like the neutrino, or relatively light things like the electron, because they have to be held together very tightly in a very small space. And Heisenberg's uncertainty principle basically tells you that if things are squeezed that close together, they tend to have a lot of energy and therefore a lot of mass. Mm-hmm. So de 't Hooft put forth a kind of guiding principle to how you might explain this, and I think we still live with that. We still don't have an easy workaround, and it turns out that this constrains things very tightly. It's very hard to build theories that satisfy these rules that de 't Hooft laid down. Now, could he be wrong? Could he have been wrong? Could there be a clever solution that we haven't thought of? All that could be true. Sure. But sort of my prejudice comes from people's rather exhaustive efforts to try and satisfy these constraints, or to understand why they maybe don't operate, why they're not operative somehow.
Good. I think that's a sensible reasons to at least not be enthusiastic until someone comes along with a brilliant theory, right, that satisfies all the constraints, etc. And the other idea I wanted to get on the table was grand unification, right? We've unified, Weinberg and Salam unified electromagnetism with the weak force. It's an obvious thing to try to do, to unify those in some real sense with the strong force. People tried. It's not that hard to write down models. Right. No evidence that any of those models is actually correct as yet.
Right. Well, so this is a story. This is a whole other story. It's a story, I should say, a story I love. Not so much in this book, but in my textbook, I spend a lot of time on it. It's incredibly rich. So this was first really laid out as a program by George I. and Glashow in the 1970s, who said, who basically picked up math books and said, how can we make the mathematics of the strong, weak, and electromagnetic force as it was coming to be understood, how can we put that in some kind of unified structure? And wrote something down, really beautiful with remarkable features. So it has a prediction of one of the strength of the interactions. It has a prediction that the proton is not stable, that it's an unstable radioactive particle, that we're all ultimately radioactive and doomed. Fortunately, a long time from now. But that opens up a whole other area of a way of understanding how we got here in the first place. Why there can be, how you can start with a universe which doesn't have matter, doesn't have what we call baryon number, and develop one with baryon number. So there was a prediction. They predicted that the lifetime of the proton was something like 10 to the 28th years. And people went down, and Mindscape is in the spirit of sending experiments you should or shouldn't send your friends off to do. So they went. So 10 to the 28th years is an interesting number, because if you think about a tank of water can easily have 10 to the 33 or 10 to the 35 or something atoms in it. So it has a lot of protons which can decay. And so if you sit there for a year, you should be able to see a lot of decays. So people went down deep into mines, and they looked and they didn't see. But the story was really quite interesting. And then along came supersymmetry. Supersymmetry predicted, well, either the lifetime was much shorter, which wasn't good, or was somewhat longer. So people again went down in mines, and they're still down there. But the lifetime of the proton is now known to be longer than is comfortable for these theories. And I think most of us believe that the proton is not stable. Even within the standard model, it's not really stable, but it lives a very long time. But whether we'll be able to see it is not known. But this is certainly a set of ideas which they're mathematically very beautiful. They're conceptually really beautiful. Sharp experimental prediction. And so they're really quite fascinating. Another aspect of these theories, which is quite fascinating, is that they predict the existence of magnetic monopoles, which is so that's something also when you take your first class in electricity and magnetism, you learn about Maxwell's equations, and you learn that the second of Maxwell's equations tells you there are no magnetic monopoles. Okay. And Dirac sort of figured out a workaround. And that is beautifully realized in these grand unified theories. So I'm a big fan. I should say that structure kind of fits neatly within string theory again. So it's kind of with all these features. So it might be part and parcel of the same story. It might be something on its own. It's the non-observation, the fact we haven't seen proton decay is certainly a problem for these ideas in most of the simple implementations which people have put forward.
I think it's interesting that you're using or appealing to two big ideas about theory choice, about what to be interested in. So, of course, obviously, we like our theories to be verified by data. But when you don't know what the data says and you're deciding which theories to take seriously, you mentioned two big ideas that are important enough to raise to a more explicit level. One is that all of these, in particle physics especially, when you add new particles or whatever, it affects everything. Like it spills off into everything. The Z boson is going to change its decay rate if you add new generations of neutrinos. If there are preons or something like that, that's going to affect the interactions of particles. So it all hangs together, and that really limits you in what theories you can sort of take seriously. And the other idea is that we want our theories to hang together, not just the data. So you know the preon ideas don't fit comfortably with supersymmetry and string theory, whereas the grand unification ideas do fit well, and it's perfectly legitimate to therefore give a little bit more credence to them.
Yeah, I obviously this is reflects levels of prejudice and perhaps hubris. A century from now, if people are still looking at these questions, I'm sure they will laugh at us for many of the things that we do. But I think we have to make some choices.
Yeah.
and and choices about what we think is plausible, where we invest our energies, experimentalists and theorists, and so yes, there supersymmetry, for example, has turned out to be a rich subject, independent of whether it has anything to do with nature. So it turned it. So, for example, so as I mentioned, there are questions in the strong interactions that are keeping me up nights, and some of these are related. So, for example, there are features of the feature of the strong interaction that it confines quarks is a very hard problem for the strong interactions as they actually are. For a supersymmetric version of the strong interactions, it's not such a hard problem. It's a tractable problem.
Yeah.
And you can make definite statements.
You can do the math.
And there are other features of the strong interactions that are mimicked that way. I'm sort of involved at the moment in a kind of debate with people about whether or not you can extend the supersymmetric results to non-supersymmetric cases. How or to what extent you can make those kind of statements.
Which side are you on?
This is just to say that certain there's people have spoken about this. I guess there are books about this, about the temptations of beautiful mathematics, and that subject is real, but that's a real thing, but there is physical insight that comes from understanding some of these theories. But there's certainly a good deal of hubris or potential for this in how you make these choices, and a little, I say a little bit just depends on, we have finite amount of time to investigate things, and where we choose to look is I say a story I like to tell. One of my mentors as a graduate student was a physicist named Physicist, who was Turkish originally. He was a wonderful person. He was very mathematically inclined. He loved beautiful mathematics. He seemed in some ways to be sort of a dreamy theorist, if you like. But I remember he took me out to lunch one day early in my career and encouraged me to do theoretical physics. And he talked about something he called good taste. And this is precisely, for a theorist, the question of how you choose problems to work on. And the truth of the matter is, he probably was not, in the way people use the term, the epitome of good taste, but he knew what it was.
Yeah, there you go.
And he knew, and he told me what I should do. And it was a very memorable and wonderful conversation.
I mean, the way I would put it is, because I think we're probably pretty closely aligned on these things. Beauty and elegance and sort of mathematical prettiness of a theory doesn't mean the theory is right. But given two competing theories that neither one of which we know is right or wrong, why would you spend too much time on the ugly one if you had a prettier one that you could spend time on?
Yeah, I mean, this in some ways gets back, in an ugly way, actually gets back. There may be a justification for simplicity in beauty, and that again gets to this question of the anthropic principle.
Right.
So the anthropic principle would sort of suggest that the simplest realization of some possibility that leads to whatever it is we want, planets, stars, carbon, is the most likely, because you're selecting among a vast array of things, and more complicated things that do all the things you want will be more exceptional. So in some sense, this gets back to my statement about the Higgs boson. So it was one of the reason for my statement before. If we need a Higgs boson to have life, okay, we only need one. It's hard to get one.
Yeah.
Much harder to get two. So as I say, I think so. So I would say that, for example, the discovery of a second Higgs boson at the LHC, were that to happen, would be a strong evidence against some kind of anthropic explanation of the strength of the weak force. So there's a if you like, a possibly complicated and ugly explanation for simplicity.
No, actually, I really, really like that. I want to sort of emphasize that because if you contrast the anthropic versus supersymmetry explanations for the Higgs boson, supersymmetry naturally comes along with several Higgs bosons, right? And because there's a dynamical mathematical mechanism that makes a prediction. Whereas in the anthropic case, you're just saying that the only reason this number is so tiny is because we wouldn't be here otherwise. And so it kind of will end up looking unnatural from our point of view. And so this is an experimental, we're updating our credences as we look for new particles and don't find any more Higgs bosons.
Yeah, I mean, a kind of ugly sort of story that I've occasionally contemplated for how supersymmetry might end up being, a little beyond where we expect is, suppose it is anthropic. Suppose supersymmetry itself, the scale at which it breaks, is anthropic. But suppose there's some other issues, but in addition to the strength of the weak force, suppose also there's, for example, some feature of the dark matter, which is important for formation of galaxies in our existence. And suppose somehow that selects somewhat larger scales of supersymmetry breaking. So it somehow scales. So suppose the dark matter comes from these extra particles of supersymmetry, as people have suggested. But suppose somehow that these things need to be a bit heavier than we guessed. Maybe that pushes things up a bit, and then we would find these other Higgs, for example, at this higher scale, as well as some of these other partners.
Yeah.
So there could be a kind of hybrid story. And, as I say, I mean, getting back to anthropics, I mean, this argument that maybe there's some kind of supersymmetry anthropically because the universe has to live a long time is an example of an anthropic argument. It doesn't predict necessarily by itself that we should be that supersymmetry is around the corner. Supersymmetry just has to be, it could be quite a high scale. It just can't be extremely, extremely high.
Let me just, because I think that I don't exactly, maybe I'm not as familiar as I should be with this particular argument, is the idea, so we have the idea that the vacuum energy, the dark energy, the cosmological constant could have different values depending on what different fields in the universe are doing. We have a particular value here, which is positive but low in our universe.
Right.
And maybe if with different field configurations, there could be either lower but still positive or even negative values of the vacuum energy. Are you saying that without supersymmetry, we should quickly decay into one of those either lower but positive or negative values?
That's what I'm saying. I should say, by the way, I had some formulation of this which was off, and the person who got me correctly situated was Edward Witten.
Okay.
And you probably know the story a bit. There's something in general relativity called the positive energy theorem.
Yeah.
Okay, which was proven, I guess, originally by Yale.
Sure, and Yale.
And for which he won the Fields Medal. And then Witten came along as a young postdoc, I think, and proved a version of this by sort of pretending there was supersymmetry. Okay, and basically the reason is that if you have a flat spacetime, a Minkowski spacetime with supersymmetry, then you can prove that the vacuum energy has to be greater than zero, greater than or equal to zero. If you break and that means that you don't have a lower energy state you can decay to.
Good.
So you can't, no matter what your theory looks like otherwise, you can't put together things in a way that you have some lower energy bubble that you can form and that grows, and which is the way the universes decay. Now, if you break supersymmetry a little bit, then you can ask, well, what happens to that? And the answer is that, well, then you typically can decay, but it takes a long time. So, and as I say, I think I blotted out the original way in which I formulated this question because it probably is too embarrassing. But as I say, it wouldn't kind of
Yeah.
got me thinking straight about this problem.
Well, more
And,
evidence that it all hangs together. We can't just
yeah,
think about these issues one by one.
yeah,
They do
yeah,
intersect with
that's
each
right.
other. One of the things, we're already an hour in, but I really want to get to some of the reasons why modern particle physicists aren't content with the standard model as a theory of everything.
Yeah,
We've given some examples of ways that we could potentially go beyond it,
right.
but I want to give more of the motivation for why we think that we're not done yet. Let me just name one: the matter-antimatter asymmetry. Right? We're
Yeah.
made of particles, not of antiparticles. How did that happen?
So in fact, I should say that these days the drivers for a lot of what's going on in theoretical physics are exactly these questions or features of, or I think people have backed away a little bit from thinking about the hierarchy problem, for example, and we're thinking more in terms of observational things we know, which we can't resolve within the standard model.
Mm-hmm.
So the so I perhaps one so a couple I've alluded to, but one in particular is the dark matter. Okay, so the dark matter almost certainly requires something new, some new laws of nature, some new particles. So that's one. Another is as you say, the asymmetry between matter and antimatter. So unless you just take that as a given, as a starting point, then within the standard model you can't explain that fact. And again, I sort of tell stories in my book about this. That the person who first sort of clearly laid out what you needed, what were the ingredients for matter-antimatter asymmetry, really formulated this question was Andrei Sakharov, who was a great Soviet scientist, a well-known dissident, called the father of the Soviet hydrogen bomb, probably not so wonderful. But in any case, he laid this out in the 60s, and he didn't really have a very plausible framework in which to consider it. The first plausible framework was, as we said, was this framework of grand unification, where people really took off with it. And subsequently, other ideas about this have arisen. And what's interesting here is, or the interesting question you might ask is, if any one of these mechanisms, so we have a bunch of plausible mechanisms for how this might come about. Can we distinguish them? Are there experimental signatures which we can hope to see, either observational signatures as we look in the sky, or things we might see in accelerators? And those questions are tough and are contingent on other things. So, for example, if we discovered supersymmetry, it opens up many possible mechanisms in which this might arise. So that's another one. Dark matter, as we've said, what is it? Is it some new type of particle? Is it some of these particles associated with supersymmetry? Is it something? I've proposed another particle known as the axion, which I think in some ways looks better, but it's also its discovery is contingent. Its discovery is possible, and there are searches that are going on, experimental searches, but success is contingent on a number of unknowns.
Well, let's be a little bit more explicit about this. I mean, let's take for granted that people think that there's dark matter. I know that not all of my audience thinks there is dark matter. Some people think it's modifying gravity, but if there is, like you say, there's good reason to believe that it's not just something in the standard model. We need to go beyond it somehow. But what are the leading alternatives for how to get dark matter out of new particle physics?
There are a number of things which people are looking at. I mentioned the axion. The axion is an idea that originated with Roberto Pache and Helen Quinn some time ago in the 70s and evolved, including inputs from myself and my colleagues Willy Fischler and Mark Strednicki and others. And if it's right, it's something that kind of emerges from actually thinking about issues in the strong interactions. And if it's right, it says the universe is made of that 20% or so of the energy density of the universe, 25% is in these particles called axions. The name comes from the name of a detergent which was popular briefly in the 70s. It's a play, it's a pun of sorts. but and in the last decade or so, we're now in a position that experiments can have some realistic chance of seeing it if we're a little bit lucky. So this is one candidate. Lately, people have sort of taken the ideas that people thought about in the framework of supersymmetry, where there were these sort of massive, very weakly interacting particles. In fact, they were called WIMPs, for weakly interacting massive particle. So people have taken that set of ideas and modified them. They've added additional particles, sometimes light particles, sometimes new photon-like particles. And people have basically opened up an array of possible explanations. My own feeling about this is, at this point, there are so many things that people talk about that one, in thinking about experiments, one wants to ask, what swath of this set of ideas can a given experiment explore?
Yeah,
because they're not so. When people first thought about supersymmetry in dark matter, it was a pretty clean story. We thought we knew what the scale of breaking of supersymmetry was, how massive these particles had to be. We had a sharp prediction of how much dark matter there was, what we should be looking for, and we don't have that at this point. So we're kind of shooting in the dark a little bit.
So yeah, with the weakly interacting massive particles, we've had two things, right? One is that we didn't see anything at the LHC beyond the ordinary Higgs, and maybe part of what we would have seen would have given us a clue to what such a particle could have been. And the other is that we've looked directly for weakly interacting massive dark matter and haven't found it yet. So it's not ruled out, but maybe this gives more emphasis to the axion idea.
My own prejudice is it gives more emphasis to the axion idea. And in fact, so the axion idea, so my own, again, this is now, I'm totally throwing my own biases in here. But the axion idea comes, as I said, it came originally from thinking about a puzzle in the strong interactions, a puzzle which is a puzzle of why the forces of the strong force isn't the same if you make a movie of some event, or isn't different rather if you look at a movie of some event and you reverse the video. You take that video and you do it backwards. Okay, so the laws of nature are the laws of the strong force is very nearly the same whether you view time as going forward or backward. Okay, it's very hard to understand that fact. Okay, the standard model is very susceptible to a breakdown of that relation between the past and the future. And the axion was proposed to explain that. There are other explanations that have been offered, and they're really sort of two. And I've spent a lot of time thinking about those two and thinking about whether they are as plausible as the axion idea. And I would claim that they're not. So if the axion is around and you need it for one thing, it might well be necessary for this other. Now, beyond that, you really need to discover it. And you're not guaranteed. You have to be a bit lucky in how things work out to be able to discover it.
Well, I think one thing maybe worth emphasizing is that even if axions and WIMPs are two of the biggest candidates for what the dark matter is, the way that experimentally we look for them is utterly different in the two cases.
No, they're very different. So for example, for the WIMPs, we look for them directly. If dark matter is WIMPs, then these things are passing through the Earth all the time. If you go down deep in a mine, with a very sensitive instrument, you can hope to see these particles. You can hope to see them once in a while. They interact very weakly, but they interact some of the time. They're sort of like neutrinos.
Yeah,
they interact sometimes, and you ought to be able to see some of those interactions. Okay, just as you can see neutrinos from the sun deep in mines, and that we've looked, and as you say, and have not seen. So we've set limits on how heavy they might be, they need to be, or how weakly they interact. Okay, and these limits are quite strong. The theories we have, the simple theories we have don't satisfy them. So we need special theories with special properties in which this would be true. Our sort of generic ideas certainly don't work. For the axion, the story is a little bit different. You don't have to go deep into a mine, but there's still axions all around us. And what you need is a big magnetic field. So an axion in a big magnetic field will convert to a photon. Will turn into a photon, a very low energy photon. Okay, so you have to have an instrument that's sensitive, a large magnetic field, and an instrument that's sensitive enough that it can detect this very low energy photon. There are other things that you need. You need, because the energy is low. There's also a particular energy you're looking for, and so you need to search in little increments of energy. Okay, very tiny increments of energy to do this. And so again, all these problems have been, for an interesting range of possible masses of the axion, have been solved. And there are active experiments. And there are ideas to look at other ranges. So I'm an advocate of a sort of lighter axion that's harder to see. And people have put forward proposals which open up some of that possible space.
Well, this discussion reminds me of a question I wanted to ask earlier but didn't. The original motivation for the axion wasn't dark matter. That was a bonus that came along. It was this lack of parity violation in the strong interactions, parity, the mirror symmetry. But the whole idea of parity in the standard model is a little bit different. I mean, a little bit weird in the sense that people were originally surprised that it was violated at all. And it's violated in a very interesting way, where the strong and electromagnetic interactions don't violate parity, but the weak ones do. Is that by itself a puzzle? Or is it just, we had a 50-50 chance of violating or not violating parity? Should we really be concentrating on trying to explain that, or just taking it as given?
It is puzzling in many ways. And it is... it actually gets back to some of our earlier discussion about why do the strong, weak, and electromagnetic interactions have the form they have. So, but it also gets back. I've mentioned string theory a couple times, and one of the interesting things about string theory, in its earliest manifestations, when people first started thinking about string theory as a theory which incorporated general relativity, was the problem of explaining this fact that that you don't have this mirror symmetry, this parity symmetry. And there were very general arguments, largely put forward by Ed Witten, that it would be very hard to construct a string theory which had this feature, that would know the difference between left and right. And the so-called first superstring revolution was the discovery that, in fact, there are string theories that have this feature. So it is a big deal to get this asymmetry. I should say, in my book, I tell a little bit of the story of the discovery of the violation of parity, both the theoretical proposal by Li and Yang and the experimental discovery by C.S. Wu. And there's actually a wonderful op-ed recently by C.S. Wu's granddaughter in the Washington Post about her grandmother and her discovery, and I felt a certain resonance with this story and the way I told it.
I told some parts of that story in my own book about the Higgs boson. It really is it's a fascinating little bit of history. But I mean, maybe this is a good entree into the final big thought I wanted to get on the table here. We mentioned string theory a bunch of times, how useful it is. But it's also gotten a lot of bad press in the public eye. I remember it must have been 10 years ago. I mentioned string theory in a non-negative way on my blog, and an editor from New Scientist said, "Oh, I didn't think that people took string theory seriously anymore. Could you please write an article for us saying that string theory is still alive and kicking?" And this is 10 years ago. So, I mean, maybe for the people out there who've mostly heard the public debate about this, what is your insider's take on string theory and its current status?
It's a good question. There's probably a fast answer and a long answer, and the long answer is in a couple chapters in my book.
Mm-hmm. That's fair.
The short answer is that string theory, I think at the moment, for many of us, and certainly for me, functions as a model of what an ultimate theory sort of might look like. Actually implementing it as a model of nature faces many obstacles. The subject is a very active one because there are, first of all, there are many theoretical questions that one can look at with in a very substantive way. And I think that's a lot of where activity is at the moment. So, for example, Stephen Hawking raised questions about the compatibility of black holes in quantum mechanics. Mm-hmm. In string theory, those questions are at least partially answered. Okay, so his objections should apply there, and they don't. Okay, exactly how string theory evades the issues he raises, that it does, I should say that it does evade them, is clear. Exactly how it does it is more mysterious, and it occupies a lot of attention of a lot of very clever people. So that's one area. String theory as a theory of nature, I think, is there's a lot of there are people who work sort of actively trying to on what they would call a string phenomenology, mm-hmm. But I think that at the moment this is a hard topic. We just don't understand well enough how in detail the theory could be related to nature. The theory is in some ways it's very simple. It postulates the basic objects are strings. Strings are rather simple things. But the steps from there to things that look like the standard model, that look like general relativity, are pretty elaborate. And along the way, there are steps we don't really understand. So it's a hard problem in the technical sense of hard, and it's a hard problem in some ways. It's intellectually challenging, but it's also a hard problem in that there are steps in that process that we don't know how to fill in. And so I think as a kind of guide to our thinking, it remains a quite rich topic as a source of understanding of big questions in science. It's a resource that I don't think we're on the brink of understanding in any detailed sense how string theory might explain the world we see.
Good. I think that's a very fair overview, but let me try to be unfair. Let me ask you how you respond to sort of the hardcore critics who might say something like this. In the 1980s, first superstring revolution, people were going around saying like, yeah, we're going to unify everything. We're going to predict the mass of the electron. Everything is going to be finished in 10 years. Then not only has string theory not made any predictions that you can test at an accelerator, but once we have the landscape of string theory, we're saying that string theory is compatible with almost any set of particle physics you can have. And at that point, shouldn't you just give up and move on to something else? It's not a thing that's going to give you any testable predictions at any point in the future.
Well, I would basically say that all that is fair. And but at some gut level, I don't exactly agree. So first of all, I would say that in 1985 already, in this era of the first superstring revolution, Nathan Seiberg and I pointed out what has come to be known as the Dine-Seiberg problem. A very basic and fundamental obstacle to relating string theory to nature. And people have proposed possible solutions, some of which are interesting, but really there's, in the subsequent nearly 40 years, people have not put forward. So I'm on safe ground. I sort of took both sides of this issue. Actually, I should say, Lenny Susskind has this book called The Cosmic Landscape, and he mentions at some point a paper that I wrote with various colleagues criticizing the landscape idea, but then in a sort of footnote says, well, but Dine sort of has come around to being more interested. And
is there any way to summarize what the Dine-Seiberg problem is?
Again, this gets a few pages in my book. But it's basically the problem that one of the great things about string theory as a theory of quantum gravity is that you can calculate things. Mm-hmm. But you can only calculate things in unrealistic settings. They're interesting calculations in any case. They're calculations that in ordinary quantum field theories you wouldn't know how to do. But it's not nature. And the problem is basically one that nature has to be sitting in a place where the kind of easy calculations to do can't work.
Right. So that's not an argument that the theory is wrong, but that
it's not an argument that the theory is wrong.
Right. Even if it's right, it's going to be very hard.
It's an argument that it's hard.
Yeah. Okay. Very good. I do remember
and it's
that
hard,
one.
And it's hard, again, in this sense, it's not just a hard homework problem which keeps you up late one night. It's a hard problem in the sense it's tough to formulate.
But okay, I mean, maybe I didn't quite let you finish, but why not just give up if we think that string theory could predict anything at all, given the landscape problem?
Well, I think I think my own attitude is to sit somewhere kind of on the fence, not to devote huge amounts of energy to it, but to allow string theory to inform my thinking about various kinds of issues. So as an example, let me take a more concrete example, this axion idea.
Mm-hmm.
Okay, I talked about the axion idea as opposed to two other ideas for understanding the strong CP problem, this time reversal problem. In making that assessment, I said, well, the axion is best, but it's only best modulo a big problem the axion had, which was pointed out, stressed by John March Russell and Mark Kamiakowski, for example, many years ago. And that problem is solved within string theory. So string theory evades it. And in a way that we can understand, in a way that if the axion idea is right, whatever is the underlying theory has to do something like that. So this is a case where so I can't say there's a prediction. I don't know, because I can't say that string theory predicts the world as we see it. But if it predicts more or less the world as we see it, we can understand how axions might arise. Okay, so there are several other examples of that sort, for example, we mentioned this landscape idea. To understand, if the landscape idea is to attain some status as a scientific idea, there needs to be some kind of structure, theoretical structure, which accounts for this bizarre fact that there are many types of universes. And string theory, we're not sure, but string theory, first of all, is probably the only framework in which we have to even think about the question. And there are some indications that it might do that, there are ways in which you can see a large number of possible universes might emerge.
Well, okay, this brings up a different worry about string theory, and maybe this is the final one. The sort of conceptual issues related to quantum gravity, right? We've been trying to quantize gravity for quite a long time. There are small but vibrant communities trying to do loop quantum gravity or causal sets or something like that, which really are just trying to do gravity rather than unify everything at once.
Right.
String theory is an example where it came out of particle physics. It wasn't trying to do gravity, but gravity sort of falls into your lap when you do string theory. But there's still the worry that because the whole theory started with just asking about strings vibrating through a pre-existing space-time, it doesn't tell us much about the fundamental questions of why there is space-time, what the quantum nature of space-time itself is. It starts by talking about strings moving through a pre-existing space-time and therefore doesn't address the conceptual questions of quantum gravity. Do you consider these to be real worries, or it's just sort of a hang-up that people have from thinking about things in a different way?
Well, I wouldn't describe it as a worry, but I would describe it as true.
Okay.
That we don't, we start, certainly the way string theory is a structure we stumbled on, very much like the blind person and the elephant. As I describe it in my book, you could give this problem a certain kind of textbook problem to a graduate student, and the graduate student can come back in a few days and tell you they discovered general relativity, and it's pretty weird. There are other ways to view the theory which are quite interesting, and in which space-time emerges as well, I should say emerges.
Yeah.
Is the language people use. The condensed matter physicists use that language. Space-time is not the fundamental entity. It's just a feature that comes out of the theory sometimes. And notable examples of this are within the so-called ADS-CFT correspondence of Maldacena and the matrix models of Banks, Schenker, Susskind, and Fischler, and in which the things you start with don't look at all like space-time.
Right.
And I think the truth of the matter is we don't know. One of the things I sort of like to say about this is we don't know, for example, is string theory many theories or is it one theory?
Mm.
We don't really know that. And similarly, we don't. So is there, for example, one theory of quantum gravity, of which string theory represents one realization which we can understand, or are there many? And these are things we don't know the answer to. So this kind of gets back to your question of should you give up? And the answer is yes and no, I think. Yes, in the sense that tomorrow you're probably not going to be able to say this is the way nature is. But no, in the sense that you're learning a lot about what might ultimately be the structure which explains the things we see.
So, okay, I think that leads into what the final question is in terms of, again, putting our money where our mouths are. When a young student comes up to you, and a graduate student who wants to specialize in something and get their Ph.D., and they're deciding between, biophysics and astrophysics and particle theory, and they say, well, I love the ideas of particle theory. It's very exciting. And some of the ongoing ideas, axions, string theory, supersymmetry, grand unification all sound very exciting. But I'm worried that the intellectual situation 30 years from now is going to be the same as it is today, because it's very hard to make experimental progress. What do you tell that young, starry-eyed person?
Well, I think I'll refer back to my book again. I think I tried to organize the kind of questions which face us in terms of where I think the most likely areas of progress are in the sense of experimental progress, in the sense of theoretical progress, and those things may be different. And my crystal ball is probably not that great.
Mm.
But I do think there are areas in which we are making progress. So, for example, I think we will, on the experimental side, I think there's a good chance that in the coming decades we will figure out what the dark matter is. We will, on the theoretical side, we will probably make progress using tools like string theory and related ideas in understanding basic questions about quantum gravity and how it fits together. So in terms of sorting out what things one might work on, I would certainly urge a student to go into areas where either on the theory side or on the experimental side, there are prospects for real progress. There aren't guarantees, and in fact, again, I say a little bit in my book. I talk about this question of how you how you make your mark, of how you might choose in science to make a lasting contribution. So I tell a story. I refer to the fact that when students come to me, I often will say to them, "You should be so lucky as to be a footnote in the history of science." and then I very proudly take from my shelf Andrei Sakharov's memoir, where I'm a footnote.
Oh, that's very good.
And so that's this is I said this is it's a challenge. It's certainly when students really come with that sort of question, it's quite serious, and and it's their lives and the way they lead their lives that are at stake. So it's not I don't approach that lightly.
I'm very much in favor of aiming for being a footnote in the history of science. I think it's an excellent place to go. And Michael Dine, thanks very much for being very fair and being very helpful in understanding where we are right now in fundamental physics.
Well, thank you very much for having me. This has been a pleasure.